Alright, so I'm seeing this fourth degree polynomial. The fundamental theorem of algebra tells me there's going to be 4 zeros because the biggest exponent is 4. Now I probably want to do some thinking, how many of each kind are there going to be? Positive and negative real zeros. So I'm noticing if I apply Descartes' rule of signs, and I'm counting 1, 2, 3, 4 sign changes. So that tells me there could be 4 positive real zeros and 0 complex, because there's got to be no more than 4. And then there's gonna, or I could decrease by 2, so there could be 2 positive real zeros, or 2 complex, complex, so imaginaries, or it could decrease by 2 again, which tells me there could be 0 positives and 4 complex, and I really hope there aren't 4 complex zeros here. So that's the possible positive solutions. Then to test, use to apply Descartes' rule of signs to test for the number of negative zeros. We're gonna say, whoops, let's get my pen to work here. I'm going to evaluate at negative x, and the 4x to the fourth doesn't change signs. The 4x to the third becomes positive 4x to the third, because when I cube a negative, it turns positive. Then I'm 13x squared won't change because of the squaring. But negative 12 times negative x turns to positive 12x. Then plus 3, that doesn't change. So I'm seeing no sign changes here. So that tells me there's going to be 0 negative solutions. 0 negative positive solutions. Okay, so I guess we're back to the drawing board. Now, we could, at this point in time, we could certainly graph it and look for some real zeros. That wouldn't be wrong. You could also use the rational root theorem, where you do the factors of 3 over the factors of 4. I might try it that way just to see. Out and graph it out at Desmos, and what I'm seeing is a double root at x equals 1/2. So that kind of confirms that Descartes rule of signs, where it says there is 2 real positive numbers, or zeros. Okay, now they're not 4, but there's 2. So now we want to be able to find all zeros. So, and I know 1/2 is a double root. So let's do some work with that. So I'm going to stop this for a minute. Okay, so now I'll do the synthetic division. That leaves me what? 4, and 4 times 1/2 is 2, and that's negative 2, and 2 times 1/2 is negative 2 times 1/2 is negative 1, and that gives me 12, and 12 times 1/2 is 6, and that gives me negative 6, and negative 6 times 1/2 is negative 3, and that is 0. So that checks, so that is a 0. And then since we knew it was a double zero, a double root, I'm going to run it right through again. So that's 2. That's 0. That's going to be 0. That's 12. Half of that is 6. And that's going to be, half of that is 6. What are 12? Just a minute here. So that's 6. So that's 0. So that checks. So what's left? I had a fourth degree equation to start with. I divided off an x twice. That leaves me an x squared left. So I've got 4x squared plus 12 as a remainder, and I'm seeing I could factor out of 4. So that leaves me x squared plus 3. Now I want to see when that's equal to 0, right? I want to find out with the 0. So if I factor out of 4 and divide 0 both sides of this equation by 4, it's gone. So doesn't that leave me x squared equals negative 3, and if I take the square root, I'm going to get x equals plus or minus I square roots of 3. So there's my 2 other zeros. So I've got 1/2 counts twice, and plus or minus I root 3 is the other 2 zeros. Now to write this in factored form, I have to do the following. Okay, so I've got these two zeros. I need to set these as factors. So what I'm going to do with x equals 1/2, I'm going to multiply both sides by 2. And I'll subtract 1. And there's the double root. Then for this one, the imaginary number is coming from taking the square root. So what I'm going to do, I'm going to do a couple of things here. I'm going to move that I back underneath the square root sign. That gives me this plus or minus the square root of -3. Now I'm going to square both sides of this equation. So that gives me x squared. Now when I square square root, those are inverse operations. They cancel each other off. If I square a positive number here, let me get a pointer going here. If I square a positive number, it's positive. If I square a negative number, it's also positive. So that gets rid of the plus and the minus, basically. That's going to give me equals -3, and then I'm going to do x squared plus 3 equals 0. And of course that's where my double root's coming from. So how does this factor out? This factors out to be 2x minus 1 squared times x squared plus 3. So that's the factored form of this. Now I think factored, what does it say, completely factored over the complex numbers. So maybe what I got to do is do this in a little bit different form. So I've got that 2x, what was it, plus 1? Yes, no, minus 1 squared. Well, that's going to factor to 2x minus 1 times 2x minus 1. And then since I have, if I go back to that plus or minus square root of I thing, I've got positive I root 3, and I've got negative I root 3. So if I want to write those as factors, all I've got to do is move those over to the other side. And the other one will become x plus I square root of 3. So now that way, this is factored, and I see my 4 zeros. They're factored. I got it factored over the complex numbers like what the directions wanted me to. So that's another form of writing this polynomial. So hopefully that helps give you a little more practice, a little insight. Descartes' rule of signs pretty cool because it helps us clue us in where we're going with it. Like I said, it's old math though. We don't have to worry about Descartes' rule of signs.